Okay, this video is quite simply just an introduction to NMR for A-level. Okay, first of all, we just need to think about electron withdrawn groups and electron donating groups. First of all, electron withdrawn groups, they have a negative inductive effect. Okay, so in terms of NMR, they cause carbons and hydrogens to appear at higher chemical shifts. So an example of a few groups are carboxylic acid or an ester. These halogens, apart from iodine, aldehydes, ketones, alcohols, ethers, nitro groups, amines, alkenes, and aromatic groups. A electron donating group will have a positive inductive effect. Okay, so these will cause both carbons and hydrogens to have a lower chemical shift value, i.e. that is closer to zero. So essentially we're talking about any alkyl group. Okay. Just a brief mention about carbon. If you have two carbon atoms which are in exactly the same environment, that is to say, they are bonded to the same atoms and are near exactly the same groups, they are said to be equivalent. Okay? So, equivalent carbons will create only one signal in the carbon 13 NMR spectrum. So, for example, if you think about butane, CH3, CH2, CH2, CH3, the two methyl groups are in equivalent environments, so therefore there will only be one carbon peak in the carbon 13 for the methyl groups. There will be only one peak for the CH2 groups as well. Okay. Another example might be the three methyl groups in 2-methyl propan 2-ol. Those three carbons, the three methyl carbons here, are exactly equivalent. There will be another peak in the carbon 13 NMR due to the presence of this carbon. So in total, although there are 4 carbons in your molecule, there will only be 2 peaks. Okay. And just make sure that you're familiar with the data sheet before the exam. So here we've got the carbon 13 NMR chemical shift data. So we're saying that closer you are, so the more electron donating groups which have a positive inductive effect will give you a lower value. It's just an empirical rule, not hard. It's not hard and fast. So again, so some peaks may appear at a lower chemical shift value than perhaps you might think. Okay, but certainly the diagnostic peaks are the esters and acids, aldehydes and ketones, very high up. Okay, now turning to our attention to the proton NMR. Okay, now proton NMR is a fabulous tool because it contains so much information. So I'm just going to spend the next few slides trying to break down those different pieces of information. So the first one, and I think this is really important in getting to grips with interpretation, is what we call either the peak area, the integration, or the integration ratios. It depends on what information is being given to you. But essentially, whatever the name is, this tells you the number of equivalent hydrogens on a carbon or on a number of carbons in a particular environment. So for example, if you've got propane, CH3, CH2, CH3, the CH2 group, or these two hydrogens in the middle, will have a peak area or an integration equivalent to 2 hydrogens. The two CH3 groups, the methyl groups in propane, they are equivalent. So they will have an integration ratio of, an integration value of 6 hydrogens. Now, it depends on how the information is presented. Sometimes it will tell you how many hydrogens are there. Sometimes the information will be given as a ratio. So for example, it could be given as a ratio of 1 to 3. So the CH2 is 1, the methyl group's 3. Or it could be a little more complicated, where you've got 0.8 and 2.4. And at that point you've got to use a bit of your chemical nous to come up with the actual number of hydrogens. Usually you'll be given a molecular formula if you're given a ratio. Next, the splitting patterns. Now this is the bit that caused the most consternation, the most confusion, because this doesn't tell us the information about the particular hydrogen or the hydrogens which give rise to the signal. It tells us the information about the number of hydrogens on the adjacent carbon or adjacent carbons. Okay. Now, there are 4 main peaks, signal types that we need to be aware of. A singlet, there is no hydrogen on an adjacent carbon. A doublet, there's 1 hydrogen on an adjacent carbon. A triplet will be caused by 2 hydrogens on an adjacent carbon, and a quartet would give rise to 3 hydrogens on an adjacent carbon. As far as A level goes, really that should be as much as you would see. However, sometimes there might be a multiplet. We use this generally speaking if there's 4 or more hydrogens on an adjacent carbon. So for example, it might be that you've got a hydrogen attached to this carbon here, and it observes 6 equivalent hydrogens. So that would give rise to a heptet, but that can be quite difficult to see, so it would be seen as a multiplet. Similarly here, if you had a hydrogen on this carbon and you had 3 methyl groups, then you would see a decat, which again, very difficult to see. Remember that the signal is given by the n+1 rule, i.e. that there is 1 more peak in that signal there is 1 more peak in the signal than there are hydrogens on the adjacent carbon. So that's why we get 2 lines when there's only 1 hydrogen next door, 3 lines when there's only 2 hydrogens next door, 4 lines when there's only 3 lines next door. We get a singlet when there's no hydrogens next door on a carbon, because we have to have a zone for that signal itself. Okay, chemical shift values. Again, very similar to the carbon-13. It depends on the environment they are in. So as we said at the start, if we're next to an electron withdrawing group, the higher the chemical shift value, further it is downfield. So for example, a CH2 next to an oxygen, for say an alcohol or an ether, you would expect in the region of 3.1 to 3.9 ppm. Whereas if you had a CH2 next to a CH3 group, then you would expect that in a 1.2 to 1.4 ppm. So again, those chemical shift values do give us a lot of information too. Okay. And again, this is the table we need to be concentrating on in our exam. Certainly the one thing to look out for, often confused, aldehyde protons 9 to 10 versus carboxylic acid protons 10 to 12. Also, a hydrogen on a carbon adjacent to an oxygen of an ester, which is a slightly higher range than if you're next door to, if your hydrogen's on a carbon attached to an oxygen, which is either an alcohol or an ether. Okay. The other thing to draw your attention to is alcohols have a broad range anywhere in there, and also amines. Okay, but OHs and NH2s tend to be a little bit broader. Okay, in the next video on NMR, we'll look at some slides about putting all this information together, and how is it that we can come up with a structure based on just a simple table of data like this. Okay, thank you for watching.